Welcome back to Multivariate Calculus. In this video, we're going to be talking about partial derivatives. In the work that we have done so far with functions of several variables, just thinking about the shapes of the graphs, you run very quickly into one of the biggest problems with trying to analyze um, planar curves instead of linear curves. Right? Curves that form a surface can vary differently in different directions, right? A curve can be very steep in one direction and very shallow in the other direction, and still come together smoothly to create the full surface. This is something you're very familiar with just looking at our world. If you've ever been near a mountain or even a large hill, you've probably noticed that going along one direction, you can find where you don't have to go up or down the hill. And there's another direction, which is usually perpendicular to that, where you have to go very steeply up or down the hill in order to make any progress. And so when we think about differentiation, when we think about the derivative of a function of a single variable, we run into the issue that we're trying to describe how much the curve is tilted, how steep it is. And there's just too many variables to do that with a surface, with a function of several variables. So we have to cheat a little bit. Instead of looking at a derivative as a generalized tool, we're going to look at things in slightly different orientations. All right, so I'm going to look down on three-dimensional space so that I have my x and y axes arranged as usual, and the z-axis then is coming right towards you. And as I analyze this curve, I'm going to analyze looking along different paths. And to describe the plane that we're talking about, we need two paths. One of those paths can go along the x direction, and the other path can go along the y direction. When we talked about limits, we talked about coming towards a point following every different possible path. When we're talking about analyzing this, it turns out that as long as we have two directions, we're going to be good to go. Because two-dimensional space needs two measurements to describe it entirely. Three-dimensional space needs three measurements. That's where the name comes from. And so the same way that we look at for a function of a single variable, the derivative of f with respect to x is the limit as some delta x goes to 0 of f of x plus delta x minus f of x all over delta x. We're going to do that looking specifically along the x direction and then looking specifically along the y direction, to emphasize that we are only looking at the derivative going in a single direction. Instead of using the symbol d that we always used for the derivative, we're going to use this symbol, which is kind of a curly d, and it's read as partial. So partial f partial x will be the limit as delta x goes to 0 of f of x plus delta x. But I said here that f is a function in two variables. So I need something for x, and I also need something for y. We're going to simply leave y alone. And if we have a partial derivative with respect to x, then we should also have a partial derivative with respect to y. Now, if you stop and you look at these definitions, right? I'd like to be on the screen and talking to you, but I guess I don't really fit with all of these definitions on the screen as well. But what I want you to notice is that it's the same definition. In this definition, for the partial derivative of f with respect to x, y just hangs out. We don't touch y at all in this definition. In this definition, we play around with the change in y, we don't touch x. So a simple way of remembering what the partial derivative is trying to do, when we take the partial derivative of a function with respect to x, we're going to pretend that y is a constant value. When we take the partial derivative of a function with respect to y, we're going to pretend that x is a constant value. And we'll treat every variable except for the one that we are taking the derivative with respect to as a constant. So if I get my head out of the way, if we have a function, f of x and y is equal to x squared y cubed minus 7x cubed plus 5y squared. Relatively simple polynomial in two variables. If I want to take the partial derivative of this function with respect to x, pretend that y is a constant and differentiate with respect to x. Term by term. In the first term, I have x squared being multiplied by some constant. The rules of differentiation say leave the constant alone and then differentiate the variable factor. The derivative of x squared is 2x. In the second term, 7x cubed, there is no y in this term, so I treat this the same way I would treat it taking the derivative of a function of a single variable. 21x squared. And then my last term, 5y squared. When I'm taking the derivative with respect to x, that means that y is a constant. There is no x in this term. This is a constant term with respect to x. And the derivative of a constant term is 0. Then when I take the partial derivative of my function with respect to y, I do the same thing, but with the other perspective. When I'm taking the derivative with respect to y, that means that x is a constant value. And a constant factor in front of a function just hangs around. So x squared will stay x squared. The derivative of y cubed is 3y squared. So that first term becomes 3x squared y squared. The second term, when I'm differentiating with respect to y, x is constant. So this whole term is a constant, and the derivative of a constant is 0. I go on to the last term, 5y squared. There's no x involved whatsoever, so we can take the derivative here the same way we would take the derivative of a function of a single variable. Derivative of 5y squared is 10y. We can do this no matter what variables the function is behaved or defined in front of. So if I have a function of 3 variables, f of x, y, and z, I can differentiate this with respect to x. First term, derivative of x is 1 multiplied by a bunch of constants is just still multiplied by a bunch of constants, so I get y and z. Second term, derivative of x cubed is 3x squared. Next term, y cubed is constant with respect to x, and the derivative of a constant is 0. Likewise, the z cubed. I can take the derivative of f with respect to y. I will get xz minus 3y squared. And I can take the derivative of my function f with respect to z, and I'll get xy minus 3z squared. Right. So the partial derivative, again, if you have a function with several variables in it and you want to take a partial derivative, you take the derivative with respect to one term and you leave the other terms alone as though they were constants. Um, we've dealt with derivatives where we had parameters in them, right? If f of x is equal to ax squared plus b, we could still take the derivative there. It's the same idea happening here when we take partial derivatives. All right. There are three notations that are commonly used for a partial derivative. The one that I've been talking about, partial f over partial x, looks like the fractional notation that we've used before. The second one is commonly used, especially in the study of partial differential equations. Um, and that's the closest analog we have to a prime. The advantage of this second notation is that f sub x still looks like a function, so we can evaluate it at a point xy. If we want to take partial f over partial x and use that notation and evaluate it at a particular point, we do that by drawing a vertical line and putting the point in question as a subscript on that line. It's really messy, and most people don't like it. So that's why this notation is often avoided when it comes to trying to evaluate a derivative or a partial derivative as a function in its own right. And that's actually why my favorite method is this last one, the operator partial sub x. Kind of avoids all these problems. It avoids the problem of thinking about the physical sciences. We usually use subscripts of x and y to denote the components of a vector, which is not really what we're going for here. Although you'll see in a little bit that there are times when that actually does make sense. So the operator notation, partial sub x, works a little bit better for handling those functions. This middle one is the one that our book tends to use most often. If you're studying physics or engineering, you're probably going to use this one the most often. But actually, this last one is the one that I'm going to use most frequently in this course. I think it strikes a nice balance between usability and function and getting the idea across. But I'll use them mostly interchangeably, depending on the nature of the problem. Just like when dealing with ordinary derivatives, I mix between using df over dx or f prime of x, depending on what was needed for the particular problem. So with all of that, all that we have left is for you to try one on your own. So let's clear a little bit of space here. And I would like you to take a look at the function f of x, y, and z is equal to x cosine y minus y e to the z. All right, so it's a function of three variables. It's a little bit messy. X times the cosine of y minus y times e to the z. And I would like you to find the partial with respect to x of f of x, y, and z, the partial with respect to y of f of x, y, and z, and the partial with respect to z of f of x, y, and z. All right, take a few minutes, see what you can do with that, make sure that this all makes sense to you, and I'll see you in the next video.